Hi, welcome to this session. Today we are going to discuss some more problems on higher order homogeneous recurrence relation, and we are going to discuss what are the solution for the non-homogeneous recurrence relation that we have to discuss in this session. Now here, some more problems that in the last session we completed one problem in the third order homogeneous linear recurrence relation. Now we are considering few problems. After that, we will go for the non-homogeneous linear recurrence relations. Now in this, find the general solution of the recurrence relation an plus an minus 1 minus 8an minus 2 minus 12 an minus 3. So here it is a n minus 3 will be there. So it is the third order homogeneous linear recurrence relation. Homogeneous, why I am calling? This is 0 here. So it is a third order homogeneous linear recurrence relation. Now here, what is the Cn is equals to 1. Cn minus 1 is equals to 1. Cn minus 2 is equals to minus 8. And Cn minus 3 is equals to minus 12. Now, what is the auxiliary equation is? The auxiliary equation of the given recurrence relation is Cn k cubed. So here I am just writing Cn k cubed plus Cn minus 1 k square plus Cn minus 2 k cubed plus Cn minus 3, this is k, and Cn minus 3, which is equals to 0. Now Cn is equals to 1, so I am just taking this is k cubed, and this is also 1, so it is k square, it is minus 8k, and minus 12 equals to 0. So I am just finding the auxiliary equation for the given equation. Now I have to find by trial and error. So it is a k equal to, I am just taking 1. So 1 plus 1 minus 8 minus 12, which is not equal to 0. So 1 is not root of the auxiliary equation. K equal to minus 1 if I am taking, then it is minus 1 plus 8 and minus 12, which is not equal to 0. So these are not roots. K equal to 1 is not root, and k equal to minus 1 is not a root. Now let us go for the other one, k equal to 2. So if I am taking k equal to 2, so it is 8 and plus 4 and minus 16 minus 12. So it is 12 get cancelled, this is 16 minus 16, which is not equal to 0, then it is not a root. Then k equal to minus 2 if I am taking, then it is minus 8 I am going to get, this is a plus 4 I am going to get, and this is a plus 16 I am going to get, this is a minus 12, so which is equals to 0. So it is a root. So I am just taking k equal to minus 2 is one of the root. Now by using synthetic division, I am going to find out what are the remaining roots, or how we are going to write the factors for this. So 1 minus 1 minus 8 and minus 12. Then if I am taking minus 2, then it is 0, 1, minus 2, then minus 1, then it is 2, minus 6, and it is plus 2, then it is 0. So I am going to write this as a factors as like this. So k, so this I am taking it as k plus 2 into k square minus k minus 6 equal to 0. So k plus 2 equals to 0. Subsequently, k is equals to minus 2, which is this, and k square minus k minus is say 0. So it is a k square minus 3k plus 2k minus 6 equals to 0. So k into k minus 3 plus 2 into k minus 3 equal to 0. So I am going to get k equal to minus 2 comma 3. So now here minus 2 is a repeated root. So what are the roots? K equal to minus 2, 3. So minus 2 is a repeated root. So for that, what is the solution for this? General solution. There are 3 roots are there. So a plus bn is repeated twice only. So it is a k1 minus 2 to the power of n and plus c 3 to the power of n. Suppose minus 2 is repeated 3 times, minus 2 is repeated 3 times, then I am going to write it as a plus bn plus cn square into minus 2 to the power of n. If it is repeated 3 times, it is repeated only 2 times, so I am going to write like this. So if it is repeated 3 times, this is the procedure. Okay, so this is the solution. What type of solution it is? General solution to the given recurrence relation, whatever the recurrence relation of the third order homogeneous recurrence relation. Now going for the next problem. So an plus an minus 3 equal to 0. So here cn is equals to the coefficient of an is cn minus 2, coefficient of an minus 2, there is no coefficient, cn minus 1, cn minus 1, cn minus 2, there is no coefficient for n minus 2 also, this is 0, then cn minus 3 is equals to 1, So we are going to get, this is, then what about this cn k cubed plus cn minus 1 k square plus cn minus 2 k plus cn minus 3 equal to 0, which is cn is 1, so k cubed, then this is 0, and cn minus 3 is 1, so k cubed plus 3 is equal to 1. So once k cubed is equals to 3 equal to 1, now I am going to find one root for this by using trial and error method. Simply, if I am taking k equal to minus 1, then what I am going to get? Minus 1 plus 1 equals to 0. So I can say that it is a root. K equal to minus 1 is a root. Is one root. Now, by using synthetic division. So it is a k cubed coefficient is 1, k square coefficient is no, k coefficient is no, then it is 1. So I am going to write minus 1, 0, 1, then it is minus 1, then it is minus 1, then it is plus 1, 1, minus 1, and 0. So I am going to write this as k cubed plus 1 equals to 0. This I am going to write it as k plus 1 into k square minus k plus 1 equals to 0. Then I am going to get, which implies k plus 1 equals to 0. Then k square minus k plus 1 equals to 0. So k equal to minus 1. Then it is just we are going to do by using roots. Real roots are not possible. Then I am going to find out the imaginary roots. So by using minus b plus or minus, so minus b plus or minus b square minus 4ac by 2a. So this is 1 plus or minus root 3i by 2. Root 3i by 2. So this is the complex root. So what I am going to get? 1 plus root 3i by 2. And next another one is 1 minus root 3i by 2. Root 3i by 2. Now, so what is the solution for this? What is the solution for this is equals to an is equals to a k1 to the power of minus 1 to the power of n plus b. Sorry, this is a complex conjugate. So r to the power of n. Then let us assume that the other constants are c1 cos n theta plus c2 sin n theta. Now I am going to find out what is r and what is the theta. In this and this are unknown, these two are unknown. Now I am going to find out what are the values of r and theta. So r is equals to modulus of k1. So if I am taking this as k1, this as k2, or modulus of k2, anything I can consider, which is a square root of real part whole square. What is that? Real part whole square is equals to, I am going to consider this as 1 by 2. Anyhow, 1 by 2 will be there common. Okay. I am just taking 1 by 4, 1 by 2 square root and root 3 by 2 square root. So it is nothing but 3 by 4. 3 by 4. So subsequently I am going to get it as 1. 4 by 4. Root of 4 by 4, it is nothing but 1 plus 3 is 4 by 4 is 1. So I am going to get r value is 1. And what about the theta is equals to, or I am just taking tan theta is equals to, then I am going to consider the imaginary part by the real part. What is the imaginary part? Let us say root 3 by 2 by the real part is 1 by 2. Root 3 by 2 is the imaginary part. So I am taking it as a p plus iq in the last my videos. Just you observe, if I am going to take in this form, then tan theta is equals to q by p, or theta is equals to tan inverse q by p, in that order. So these two get cancelled. Now it is equals to root 3. Now what about theta is equals to tan inverse root 3, tan inverse root 3, which is equals to pi by 6. So now what is this equation will become? This solution will become an is equals to a minus 1 to the power of n plus r to the power of n. It is nothing but 1. 1 to the power of n is 1 only, and c1 cos n theta n pi by 6 plus c2 sin n pi by 6. So this is the general solution for the given recurrence relation an plus an minus 3 is equals to 0. Is equals to 0. Now we go for the another problem. Let us consider the other recurrence relation. Now observe this recurrence relation and the previous recurrence relation. This is n minus 3 will be there, and here it will be n minus 4 will be there. So it is known as, it is nothing but a fourth order linear homogeneous recurrence relation. This is the fourth order. This is the fourth order homogeneous recurrence relation. So here, what are Cn is equals to? Cn is 1. Cn minus 1 is, there is no n minus 1 term. Cn minus 2 is minus 7. Cn minus 3, there is no term. Cn minus 4, it is 10. Then what is the auxiliary equation? The auxiliary equation will become C1, Cn k to the power of 4 plus Cn minus 1 k cubed plus Cn minus 2 k square plus Cn minus 3 k plus Cn minus 4 equals to 0. So C1 is k to the power of 4, and there is no Cn minus 1 minus 7k square, and there is no term of Cn minus 3, and Cn minus 4 is a 10, so which is equals to 0. So this is k power 4 minus 7k square plus 10 is equals to 0. Now let us assume that if I am going to take it as k square is equals to, let us consider k square is equals to p. then this will become p square minus 7p plus 10 equals to 0. So this is nothing but p square minus 5p minus 2p plus 10 equals to 0. So p into p minus 5 and minus 2 into p minus 5 equals to 0. So p equals to 2 and it is 5. So what is p is k square. So if p is equals to 2, then k square is equals to 2. So what about k is plus or minus root 2. And if this is one value, if p is equals to 5, k square is equals to 5, k equals to plus or minus root 5. So 4 roots are there. All roots are real and distinct. Then the solution of this is, so 4 roots are there means 4 constants will be there. Say a k1 to the power of, let us assume that the k1 is equals to root 2. k1 is equals to root 2 and k2 is equals to minus root 2 and k3 is equals to root 5 and k4 is equals to minus root 5. So substitute this. This is root 2 whole to the power of n plus b minus root 2 whole to the power of n, c root 5 whole to the power of n plus d minus root 5 whole to the power of n. So this is the general solution for the fourth order, given fourth order homogeneous recurrence relation. Homogeneous recurrence relation. So in this way, we are going to calculate, we are going to find the solution for homogeneous, whether it is the second order or it is the third order or it is fourth order or in general if it is the kth order. So this is the procedure to find out the general solution as well as the particular solution. Whenever conditions are given, then we have to calculate A, B, C, D. So to find the 4 constants, we need 4 values. So if it is given as A0 value, A1 value, A2 value, A3 value, A3 value, then it is possible to calculate. That means A0 to A3, if they are given, then it is possible to calculate A, B, C, Ds. After that, if you are going to substitute in this expression, then it is nothing but a particular solution for the given recurrence relation. Now, this is the study that we are going to concentrate, how to solve a homogeneous recurrence relation. Now we are going to concentrate a non-homogeneous linear recurrence relation. So now we are going to consider a recurrence relation of this form. So the difference is here, there is no 0. Here f of n will be there. Here f of n will be there. So then this is nth order. So, this is n minus k will be there. So kth order non-homogeneous recurrence relation with constant coefficients. Why I am taking with the constant coefficients? Because Cn minus 1, Cn minus 2 and so on, Cn minus k are constants. So we are calling it as a constant coefficients. So to solve any non-homogeneous linear recurrence relation, the solution must be of this form. So here what is this? An to the power of h and an to the power of p. So an to the power of h is nothing but the general solution for the homogeneous equation. Homogeneous equation means you made f of n is equal to 0 and write the auxiliary equation and find the roots, and according to the roots you are going to write its general solution for homogeneous. So that is nothing but the solution an power h. This is nothing but solution for the homogeneous. And next, this is the other solution. An power p is called a particular solution of the relation, of the recurrence relation. So whenever this is one solution and this is another solution of any recurrence relation, then the linear combination or else the combination is again a solution for this. This is, we know how to find out a n power h, how to find out the solution for the homogeneous recurrence relation. Now we are going to find how to find out a particular solution, how to find out a particular solution. Now, there are some rules will be there. There are 4 different cases we are going to considering here. There are many cases exist, but we are going to consider only 4 special cases of these special cases, and a straightforward way that we are going to find out by taking 4 special cases. First, case 1. In this case, f of m is a polynomial. That means the right side, whatever the function is given, this is f of n is a polynomial, of degree q, and this is important. 1 is not root of the auxiliary equation, or 1 is not root of the characteristic equation. 1 is not root of the characteristic equation, and f of n is a polynomial of degree q. Then the assumed particular integral as a n to the power of n is equals to a naught a1n plus a2 n square and so on, aq n to the power of q. aq n to the power of q. If it is a polynomial of degree q, up to that we have to extend. And here a0, a1, a2 and so on, aq, all are constants. Treat this as the solution for the given recurrence relation and substitute. Then we have to find out what is the value of a0, a1, a2 and so on, aq, and afterwards we are going to substitute into this expression. Then whatever the result we are going to get, that result is nothing but a particular solution. Now here, this is here we should not keep all this same way, because if I am going to consider a second order recurrence relation, there are already 2 constants will be there in the homogeneous solution. But if I am going to consider some more constants in the particular solution, and it is not the solution for the recurrence relation, so it should be free from the constants. So you need to calculate what is a0, what is a1, what is a2 and so on, what is aq. After that we are going to substitute in this expression. Subsequently we came to know what is n to the power of p. So this is true if 1 is not root of the auxiliary equation or characteristic equation. So if suppose 1 is the root, and f of n is the polynomial of degree q, and 1 is the root. 1 is the root means how many times it is repeated. If it is a simple root, or it is a repeated root, or it is repeated 2 times, it is repeated 3 times and so on. So let us assume that it is repeated m times. M may be 1, m may be 2, m may be 3, whatever the value will be. So f of n is a polynomial of degree q, and 1 is the root of the characteristic equation or auxiliary equation, and 1 is repeated m times. Then what is the assumed particular integral? What is the assumed particular solution? So whatever there earlier, so for that we are going to multiply with n to the power of m. If it is a simple root, 1 is only simple root, then I am going to take m is equal to 1. That means n into the whole thing. We have to consider. If 1 is a repeated root, that is m is equal to 2, then I am taking n square into this. If 1 is repeated 3 times, n cubed into this we have to write. Suppose if it is not there, what happened? It is going to be satisfied and it is not possible to calculate what are A0, A1, A2 and so on, AQ values. AQ values. So it should be must and should we have to multiply whatever the assumed particular solution will be there. So for that we are going to multiply with n to the power of m and we are going to consider the whole expression as a particular solution. And after you just substitute the whole expression into the equation and we came to know what is A0, A1, A2 and so on, AQ. After that we have to substitute in the assumed particular solution. So this is the case 2. And now case 3. What is the case 3? Suppose in these two cases what we discussed, f of n is a polynomial of degree n, degree q. Suppose if it is not a polynomial of degree q, let us, I am just taking, it is, let us, which is of the form 2x square, 2x square or x to the power of 6 or 3x cubed. Like that it will be there and the n cubed, like not x, f of n is a function of n cubed, n square or 2n square, 3n square, like that it will be there. Then how to assume a particular solution? How to assume a particular solution? So in such a case, let us consider alpha b power n. Alpha is any constant like 2, 3, 4 and so on. And b is not root of the characteristic equation or auxiliary equation of the homogeneous. When we say that it is a root, whenever you are going to find the homogeneous part, homogeneous solution, in that we are going to find out the roots as we discussed in the previous sessions, and how to write the an to the power of h we discussed there. So just accordingly we are going to say that what are the roots. So we are going to find out what are the roots, whether b is a root or not of the auxiliary equation. If it is not root, then we are going to assume this is the particular solution. Once again, we are assumed that it is a particular solution, means it satisfies the given recurrence relation. It satisfies the given recurrence relation. So you have to substitute. You have to substitute in that recurrence relation, whatever the recurrence relation will be there. And suppose the recurrence relation will be an is equals to and 5 an minus 1 plus 2 an minus 2. If it is there, then I am going to substitute here this into this. And what I am going to write? An power p and is equals to 5 an minus 1 power p and 2 an minus 2 power p. And in this n is equals to n, I am going to substitute and I am going to write this. And n is equal to n minus 1 and I am substitute this. N is equals to n minus 2, I am going to write and I substitute this. And substitute this. So from this, I am going to equate the constants or whatever the variables will be there in that one. And we are going to find out what is A0. After getting A0, and we are going to substitute in this assumed particular solution. Subsequently, we can get a particular solution. So concentrate whatever the particular integral, it should be free from constants. Now the fourth case, what we discussed, we say that b is not root of the auxiliary equation or characteristic equation. Suppose b is the root of the characteristic equation. And once again, what type of root, whether it is a simple root or it is repeated m times. Let us say that b is a root of multiplicity m. b is a repeated m times. M may be 1 or 2 or 3, whatever it is. Then the assumed particular integral, which is of this form. So we are going to multiply with n power m. This is important. If it is not there, then automatically the equation it is not possible to calculate A naught or whatever the values will be there, whatever the constants will be there. So try to concentrate on this, and whether B is a root and B is not a root of the multiple auxiliary equation. If it is a root, and how many times it is repeated. Suppose if it is repeated for 2 times, then I can write it as A naught n square b to the power of n. If it is repeated 3 times, I can write it as n cubed b power n. If it is a simple root, then I can write it as n b power n. M is equal to 1 is a simple root. M is equal to 3, then I am going to write M is equals to 2, then I am going to write this. And now after finding this, then we have to substitute the into the given equation recurrence relation, and we need to calculate what is the value of A naught. What is the value of A naught? After that, we are going to substitute there. Then the final solution AN is equals to the homogeneous solution plus the particular solution. The particular solution, that is AN power P. So as we discussed in the previous one, so here the complete solution is a general solution. Whatever this is the general solution for the non-homogeneous recurrence relation. So here, how to find AN power H we know, and how to find, we are considering only some of the special cases, not all the cases, only some of the special cases, how we are going to assume a particular solution to the recurrence relation, and those 4 assumptions, those 4 special cases we have to consider, and accordingly we are going to find the appropriate appropriate constants in that. After finding the constants, and we are going to substitute those values in the assumed particular solution, then we are going to get the a particular solution. Then the general solution is nothing but a homogeneous and the particular solution. In the next class, in the next session, we are going to discuss some more. We are going to discuss by solving a problems, and how we are going to get AN power P. So with that, I am going to conclude this, and thank you.
Like, share and subscribe. Hit the bell icon for more updates.